definitely going to do some graphing of tangent and cotangent today. We're not going to do any word problems today. If we do, it's just kind of a, can you pick out the important stuff, but there's nothing in this section for that. So this says find the exact values for y equals the tangent of x. So this is where, like I said, you go back to the unit circle and you think, wait a minute, I can't do negative pi over 2 because that's going to be undefined. Because when you take y and divide it by x, the x is 0, and we can't do that. Then we have negative pi over 3, and again, you can go back to the unit circle. That comes out to negative square root of 3. And we have negative pi over 4, which worked out really nicely to negative 1. And negative pi over 6 would give us a negative square root of 3 over 3. Now, if the unit circle thing bothers you, remember you can always go back to your special right triangles. And then use our drawing of the signs, plus, 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 minus, 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 plus, and minus, plus, minus, in order to get these values. At 0, it's 0. And apparently it has nice symmetry because for pi over 6, we're going to get the square root of 3 over 3. Again, makes sense if you go over here and say, okay, pi over 6 is 30 degrees. If I want tangent, I need opposite over adjacent. That's 1 over the square root of 3. Oh yeah, that'll be the square root of 3 over 3. Pi over 4, it's 1. Opposite over adjacent. Pi over 3, again, nice symmetry with what we see here. That'll be the square root of 3. And pi over 2, because we're dividing by 0, is undefined. So that's why we see what we do up here. We've got vertical asymptotes at negative pi over 2 and pi over 2, which shows us the period for this is not 2 pi anymore. If we're going from negative pi over 2 to pi over 2, that's 1 pi. So with tangent and cotangent, our period is 1 pi. And like it says, from the table of values, we can see that the tangent of x equals the tangent of x plus pi. Because with that unit circle, as we keep going around, we're going to see those same values. So that means we will have another one over here, we'll have another one over here. But it's really just that repetition of one period that's moving from position to position. And the principal branch is the one that they've shown here, the one that's right smack dab in the middle and goes through the 0. But like I said, there's just not as much to the tangent and cotangent graphs as there are cosine and sine. So the tangent has asymptotes at the zeros of the cosine function. Why is that? Because the cosines are the x's. And when we do tangent, we're doing y over x. So anytime those x values are 0, well, that's when we're going to have an asymptote because you can't divide by 0. So looking at this drawing, what they're doing is they're helping us to see, okay, if the blue one is cosine, then there's going to have to be an asymptote right here and right here. Pi over 2 and 3 pi over 2. And yeah, on the last drawing, we saw it's negative pi over 2, pi over 2, then you have to go 1 pi more. So if you had pi over 2 and you added 2 pi over 2, now you're 3 pi over 2. And you could just keep going to get those asymptotes. Tangent will have zeros at the zeros of the sine function. And that's because sine is on the top. And if we get a 0 for sine, that means we have a 0 for tangent. So it's going to be at 0, at pi, and at 2 pi. Again, not a shocker because the period is 1 pi. So if we're at 0, 1 pi, then 2 pi, then 3 pi, then 4 pi. Y equals the tangent of x is sine of x over cosine of x. And here's what we have to get used to. negative pi over 2 and a positive pi over 2 to locate our vertical asymptotes. It's 0, the graph's a 0. At 45 degrees, it graphed as 1. Well, 45 degrees in radians would be pi over 4. It will graph as 1. And then if we go backwards to negative pi over 4, better move that so I'm not writing over the top. Because it has symmetry, it's going to graph as negative 1. And tangent is always increasing. So I start low on this side and then increase in a symmetrical curve as I go to the right. So again, I start thinking to myself, all right, since this is 1 pi now, if I wanted to do another one of these, I'd have to take pi over 2 plus 1 pi. So pi over 2 plus 2 pi over 2, that would make this one 3 pi over 2. And that would be my next asymptote. But this pattern would be exactly the same. So halfway between those two, well, let's see, if we had pi over 2 and 3 pi over 2, this is the same thing as 2 pi over 4. And this is the same thing as 6 pi over 4. So halfway between that 2 pi over 4 and that 6 pi over 4 would be 4 pi over 4, which is pi. Well, that makes perfect sense because this 0 was at 0, and it's supposed to be at multiples of pi. And then all we do is say, you know what, we're going to go over to the right 1 unit and up 1 unit. And away we go. And if we want to label those, we haven't started anyway. We said this is 2 pi over 4, so this would be 3 pi over 4. 4 pi over 4, 5 pi over 4. And you can just continue on with that pattern. So the big differences with tangent, we have asymptotes. And the period is 1 pi instead of 2. So for f of x equals the tangent of x, the period is 1 pi. 1 pi each time. Zeros are where the sign of x equals 0. Now notice how they have to put this. It says for all x's, x has to equal n pi. Let's see. 0, 1 pi, 2 pi, 3 pi, etc. And it says n is the set of all z. We have to remember from way back at the beginning of the year that z is the set of all integers. And the integers are -3, -3, -2, -1, 0, 1, 2, 3, going on for everything decimals and no fractions. So this is a way to describe that if you continued this forever, you're going to see those zeros at 0, 1 pi, 2 pi, 3 pi, 4 pi, and negative pi, negative 2 pi, negative 3 pi. It'll continue on forever. So then what on earth do we do for the vertical asymptotes? Because they're at pi over 2. Well, this is a negative 1 pi over 2. Then we have a positive pi over 2. Then we have a 3 pi over 2. So it's just using odd integers as we go through it. So that gets written this way. It's where the cosine of x equals 0. And all x's where x equals pi over 2, there's our nice starting place, plus n pi, where n is the set of all integers. There are other ways to write this. I've seen people, let's see, what have they done before? X equals pi n over 2, where n equals 0 and all odd integers. So there are different ways to write it. But we have to get across that not only are we going to be at the negative pi over 2, the pi over 2, just has to keep going. So we don't get any horizontal asymptotes. This is not bounded. You know, we're going above and below forever. And then our domain is x's such that x is not equal to anything that's vertical asymptote. So pi over 2 plus n pi, where n is the set of all integers. Our range is from negative infinity to infinity. And we're using all the y's. And as we have done in the past, we have to say that this is continuous over its domain. We know there are vertical asymptotes. You know, we know that it's going to cut it off at certain points. But those vertical asymptotes are not in its domain. So when you use the domain the way you're supposed to, then it is continuous on its domain. Symmetry. What do you think? Even, odd, neither? What do you see? Odd. Odd symmetry. It's an odd function. And that means that the tangent of negative x equals the negative tangent of x. So it doesn't matter if our negative is located with the x or if we pull it out in front. It's going to do the same thing both times. No local extremum, up and down forever. And tangent is always increasing on its intervals. Always the low to high. Not bounded. Not bounded above and below. And then do you remember what we had to say for end behavior when we did cosine and sine? Does not exist. End behavior does not exist. And that's because of that oscillation that takes place. In this case, it's because we have asymptotes, you know, it kind of cuts everything off. So we're not going to be able to do that. All right, so that was tangent. Now I start thinking cotangent. Let's see, cotangent is what you get when you flip tangent. So that means sine and cosine are going to play opposite roles for cotangent. And that's exactly what takes place. The cotangent will have zeros at the zeros of cosine. Because with cosine it's x over y, and x is cosine. So looking at cosine, I see a 0 at pi over 2 and a 0 at 3 pi over 2. Well, that's where the asymptotes were for tangent. So those have switched positions because we're turning it upside down. And then the cotangent is going to have asymptotes wherever we see sine as 0 because that's on the bottom. So for cotangent, the asymptotes are going to occur at 0, at pi, at 2 pi, at 3 pi, etc. So cotangent, asymptotes at the zeros of the sine function. So now, what do we have to really remember about tangent and cotangent? The location of the asymptotes. For tangent, it's going to be that negative pi over 2 and pi over 2. For cotangent, it's 0 and pi. A little bit easier to remember for cotangent. Right in the middle is where that 0 is going to occur. So that 0 is going to be at pi over 2. But cotangent is always decreasing over its interval. So we cut this in half again and we get our little pi over 4. But that's going to be up here at 1. And then we can put our little 3 pi over 4 halfway between pi over 2 and pi. And that's going to get us a negative 1. And then again, we just make a nice smooth curve showing that we're approaching the asymptotes. Remember, we need to spread these things out so they look like they're approaching the asymptotes, but never quite getting there. That's cotangent. If you wanted to make another one, go out to 2 pi. And you'd say to yourself, self, what's halfway between 1 pi and 2 pi? That'd be 1.5 pi, which is 3 pi over 2. Then you'd go through the same thing we did with tangent, but that pattern of back 1 and up 1 and over 1 and down 1 is going to stay the same because you get a new asymptote every time you come across a pi. Oh, it didn't hit my 0. So what people have trouble with cosine and sine is usually coming up with the labels for our integrals. Figure out the increment and find the label. It's just not going to be the same with tangent. It's going to be easier because you're constantly thinking, okay, I need to split this in half. Now I need to split this in half. And working with a half generally is not an issue for most people. So our period is pi. Zeros are where cosine equals 0. So that means that our x values are at x equals pi over 2 plus n pi. Those are our zeros that you see up there. That's what's happening at pi over 2 and 3 pi over 2. So we want to make sure that we tell people, hey, it's going to be pi over 2, it's going to be 3 pi over 2, then it's going to be 5 pi over 2. And the way that they described that was saying, you know what, just start with the first one and then say, just continue to add pi, because that's the period for this. It's going to be pi. And this is a set of all integers. And then the vertical asymptotes are, just like I said, it's a flip-flop of what we saw with tangent, where the sine of x equals 0. So that's all x, where x equals n pi, where n is the set of integers. No horizontal asymptotes, going up and down forever. Our domain is based on the asymptotes again. So that's our x's, just like, if you're having trouble seeing these in the back, this domain is exactly what you write for the set notation for those vertical asymptotes, because we want to leave those out. All you see is that there's going to be a crossed out equals when we talk about the domain. So we want to leave those vertical asymptotes out. Range negative infinity to infinity, and yes, it is continuous on its domain. Pretty obviously we have those breaks with the vertical asymptotes, but over its domain, if we leave those out, it is continuous. Symmetry. Taking a look at this one. Is it symmetric with respect to the origin? No. Is it going to be even with respect to the y-axis? It's an odd function, but it's very weird when we think about it. How does this really work? So that we get that odd symmetry. And you'll see they do have counterparts over there. It doesn't look like it when you first go to figure out, hey, is this symmetry going to work or not? But it does. So the cotangent of negative x equals the negative cotangent of x, just like our tangent piece. Local extrema, we don't get any. We're talking about infinity up and down. This one is constantly decreasing over its domain. So decreasing on each interval in its domain. It is not bounded. And just like we've had to say with the end behavior before, it does not exist. Not exist. Look at that, we're already to the examples. Anybody need more time to write anything down? All right, we're going to graph a tangent function, doggone it. It says we are going to describe the graph of y equals negative tangent of 2x in terms of a basic trigonometric function. That means we're going to describe the transformations. So what's the negative doing for us? Reflection over the x-axis. How about that 2 in front of the x? What's that do? Horizontal shrink, factor of 1/2. Horizontal shrink. Factor of 1/2. Locate the vertical asymptotes and graph 4 periods of the function. Wow. Okay, well, then why would we have to do 4 instead of 2? Because this one only has a period of 1 pi. So, start thinking, all right, for tangent, it's normally negative pi over 2 to pi over 2 for the asymptotes. That's where the location of those asymptotes are going to be. But this problem has a little 2 to put in here. So I'll just put a different color in there. Well, that means we have to divide everything by 2. So this is going to go from negative pi over 4, and again, dividing by 2 is the same thing as multiplying by 1/2, less than or equal to x, which is less than or equal to pi over 4. So, I'll label that one a negative pi over 4, I'll label this one a positive pi over 4, and I'll think about what's going to happen with my tangent graph. Those are my asymptotes. Halfway between those asymptotes is where my graph has to cross the x-axis. But this time it said I have to reflect this over the x-axis. So normally with tangent it would always be increasing. My points would have been here and here, because again, you cut it in half and you get your 1, and you cut it in half and you get your negative 1. But we have to reflect that over the x-axis, which means it's actually going to look like this. So what does a negative in front of the tangent make it look like? Cotangent. Exactly. So when you see the negative in front, you really could say to yourself, I'm just going to graph cotangent. Just do that instead. But now what we have to do is get some labels on here, and like they said, we have to go 4 periods with this. So I start thinking, between 0 and pi over 4, what's smack dab in the middle of that? What's half of pi over 4? Pi over 8. All you have to do is take it times 1/2, and that'll get it for you. So this was my negative pi over 8. Now I'm probably not going to detail each and every interval with that, but at the very least we want to label our vertical asymptotes. So we had negative pi over 4, 1 pi over 4. Where do you suppose the next one's going to be? Negative pi over 4, pi over 4. Maybe we ought to talk period. If it was pi before, and now we have that tangent of 2x in there, does everybody see that that's b? So for these, we're going to use the formula period equals pi over the absolute value of b. So yeah, we want to go by pi over 2 each time. Before we were supposed to go by pi, but this had a horizontal shrink, factor 1/2. So we're going to add a pi over 2. We've got pi over 4, add pi over 2. Think common denominators. This will give you 2 pi over 4. So we'll end at 3 pi over 4. Now maybe you can see the pattern so we don't have to do the math. Negative pi over 4, 1 pi over 4, 3 pi over 4. What would the next one be? Well, then we better do it by hand. Yes, see how it's the odd integers? Negative 1, positive 1, 3, 5. And like I said, if we have these little increments in here, then we can kind of cheat. And just keep going halfway. But I'm going to need at least one negative in order to make this the 4 periods that they wanted. So I'm at negative pi over 4. And I've got to subtract pi over 2, which again is 2 pi over 2. So negative pi over 4 minus 2 pi over 4 would give me negative 3 pi over 4. It shouldn't shock us because we talked about how it's the odds. And one more branch there. Periods. I don't like that I didn't put my third class in there. Do you see how we could call the middle one kind of the primary period? So if I do all of my labeling in here, I can get away with just putting the asymptote labels on the other ones because we can see what the intervals are as we go through there. But like I said, negative tangent is going to look like cotangent as we go through there. This one says we're going to finally graph a cotangent function. This one has a little bit more going on. We've got 3 cotangent x over 2 plus 1. And the first thing they want us to do is describe that transformation, which would be from cotangent x. So what's the 3 doing? Amplitude, which is vertical stretch. How about the 2? What's the 2 doing? Horizontal stretch. Factor of 2. Good. Remember, anything with x is the opposite of what we see. How about the plus 1? Vertical translation. Up. 1 or positive 1. Ooh, I can keep track of this one too. All right. So cotangent. The asymptotes are not at negative pi over 2 and pi over 2. They're usually at 0 and pi. But we have a little x over 2 on this one. So we're going to have to multiply everything by 2. And there is our horizontal stretch. Instead of being 1 pi, this is going to go out to 2 pi. So, did they want 4 periods? Oh, good, only 2 periods of this one. All right, so we'll start with 0, and then let's see. I hate to make it look smaller than it should be. I'm going to, for ease of graphing, I'll make this 1 pi, and this will be 2 pi. As long as we have the increments labeled, we'll be okay. So, asymptotes at 0. And at 2 pi. But we better put some helpers on this one. What's a helper we can put on? So we remember that's kind of like our new axis there. Alrighty, so what else do we need? Well, we need to know halfway between is where we're going to get our 0. So that's going to land at pi, but it's going to be up here because remember this has that vertical shift of 1. And normally, if there's no number out in front, we just kind of use the fact that there isn't a number out in front to say it's a 1. So you go over 1 and up 1. But this one has a 3. So you can kind of think of it as a slope. But cotangent, are we going to be increasing or decreasing? Decreasing. So here's what we do. We're going over, it's not 1 unit, but it's a unit with our intervals. So we're going over pi over 2 and up 1, 2, 3. And then you do the opposite to go in the other direction. So going over pi over 2 units and 1, 2, 3. I missed my point. And again, we should label those and put, hey, this is pi over 2. And I'll have to label this one up here. 3 pi over 2. But we need another period. So I definitely would go backwards on this one. 1, 2, 3, 4. So this would be my negative 2 pi. And this would be my negative pi. But we have our 0, and negative pi, and then back 1 and up 3, and to the right 1 and down 3. And that's because whatever we would get for the cotangent, we'd have to multiply it by 3. Oh, you're kidding me. Are we out of time? Well, you'll be able to start, I guess. I'm just wondering if I shouldn't just do the other ones on a video, so we don't get behind here. So try. You're going to feel like a lot of the steps that we had to do with cosine and sine are a lot easier now because the increments are about splitting things in half each time.
Your homework is to be like all graphic.
I mean, there were 4 graphs. 4 of them on the assignment.
There will be a tech meeting for Shrek the Musical today after school from 2:30 to 4 o'clock. Meet in front of the Zadie Theater.
So,
Again, there will be a tech meeting for Shrek the Musical today